Alrighty, so now we have section 5.3, which is about a distribution called the Poisson distribution. Right. So the Poisson distribution is another distribution that counts, right, like the binomial distribution, but it counts the number of successes. And again here, successes is sort of a biasing word. We don't necessarily mean a positive event, but it's the event that we're counting, and we just call it a success. Over time, right? And the first rule is that the events we're counting need to be independent. And the average number of successes in an interval should be constant, and they use the Greek letter lambda to stand in for it, right? So if you're talking about a Poisson distribution, then your lambda is going to be the main distinguishing point of it, right? Before we had n and p, and that told us everything we need to know about a binomial distribution. Poisson distributions, lambda tells us everything we need to know, right? And it's super nice about it too, because lambda is what mu is. It's what the expected value is. It's also what the variance is. And the probability is not quite so nice, but it's also not too bad. E, that's a horrible looking E. E to the negative lambda, lambda to the x, all over x factorial again. Remember, x factorial is x times x minus 1 times x minus 2, so on and so forth until you get all the way down to 1. So you can use your calculator as before. I won't be able to here, but if we go to distributions again, and you look down here at C and D, it says Poisson PDF and Poisson CDF. So you're going to use them. Let me write it out. The probability that x is equal to x is Poisson PDF, and you put lambda in here, and then you put x. The probability that x is less than or equal to x is Poisson CDF of lambda and x. Right, and the same rules apply if you want to talk about a greater than, right? Probability that x is greater than x. This is going to be 1 minus the probability that x is strictly less than x, which is 1 minus the probability that x is less than or equal to x minus 1, which is 1 minus Poisson CDF lambda x minus 1. Right? So exact same sort of way that you use it. It's just going to be a matter of looking for Poisson, PDF, and CDF instead of binomial CDF and BDF. So one of the key things is that this interval that you find for lambda needs to be the same one as the problem. Right, so we'll go through an example here. We'll go through one problem like we did before. So So on a particular day, McDonald's has an average of 4 cars per 20 minutes through the drive-thru. So what is the probability of getting 10 cars in 1 hour less than 8 in an hour more than 11 in an hour? Right? So the first problem that we see here, right, this is a Poisson distribution because we're counting the number of successes, which in this case is cars that drive through the drive-through over a particular amount of time. But the key thing we have to look at, we need to figure out what lambda is. And it looks like lambda is 4, right? If we just read that far, lambda is supposed to be the average number you get per interval, and it's telling us it gets an average of 4. But we notice that 4 is per 20 minutes, and all of our questions are per hour, right? So that means that we need to figure out what is the average per hour based on the information we have. Well, if it's 4 every 20 minutes, and an hour is 60 minutes, so it's 4 cars per 20 minutes. And we want to get cars per 60 minutes, right? We need to multiply top and bottom by 3, right? Because we need to multiply 20 by 3 to get to 60. So if we multiply the bottom by something, we have to multiply the top by something. So lambda is going to be 12. Right? So then we would say the probability of x equaling 10 is, well, we could plug it into that formula. We'd get e to the negative 12, 12 to the 10, all over 10 factorial, and we could plug that into our calculator. Or we could plug Poisson PDF of 12 for lambda, 10 for x, and see what value it gives us. Right? The other question is asking what's the probability that we get less than 8 in an hour? Right? Again, to talk about the CDF, we have to have a less than or equal to. So we translate this to being less than or equal to 7, because if all you have is counting numbers, then less than or equal to 7 is the exact same thing as strictly less than 8. And we know that we need Poisson CDF, lambda again, and 7 this time because of our x there. Right, and lastly, the probability that x is greater than 11. Well, that's going to be 1 minus the probability that x is less than or equal to 11, right? Because these two events are complements of one another. So if you subtract 1 from 1, you get the other. 1 from the number 1. So this is going to be 1 minus Poisson CDF 12, 11. All right. And that's what we would plug into our calculator. I'm sorry that I can't plug it into my calculator, but hopefully it's easy enough to find those buttons. And so last section I said that for the binomial you could just add these up. It's a little bit tricky with Poisson because you go all the way up to infinity, right? Binomial, the highest thing you can get is n. For Poisson, you can technically go all the way up to infinity. So something like this, you'd have to, something like this, you'd have to translate to this first, and then you'd have to add up 11 different possibilities, subtract all of them from 1, All of your possibilities look as nasty as that thing. So I really strongly recommend becoming comfortable with using the distribution button on your calculator. So next week we will be doing, next week's homework is starting off doing some normal distribution stuff. So we'll talk about a continuous random variable. So I'll see y'all then.